Hello students, welcome to Math 3410 Differential Equations, Lesson 2a, Separable Equations. Finally, we are beginning to learn how to solve a differential equation. The topic here today is separable equations, and this is going to be the easiest class of differential equations to solve, but at the same time, it's going to be one of the hardest to analyze. So it's going to be the easiest and also one of the hardest at the same time. Let's do the easy part first. Here's a typical form of separable equation. T part and y part are completely separated like this. And then what do? Divide everything by g of y so that we have only y's in the left-hand side and t's in the right-hand side. And then we take the antiderivatives, and what do we have? We have an implicit solution. Many times that's going to be sufficient. In some cases, however, we have to do a little bit further and try to get explicit solutions. Now, that's when the interval of definitions and some other things may come into play. So you have to be a little bit careful there. As far as the separation of variable, this kind of trick, and then taking the antiderivative, no problem. Okay, let's go to some example problems here, and let's begin with something easy. Okay, how to solve this? Separation of variable, all the y's on one side, all the x's on the other side. So y dy is equal to negative x dx. And then we take the antiderivatives. All right. What's the antiderivative of y? 1/2 y squared. And that is equal to negative of 1/2 x squared, and then we're going to need an integral constant c. So there goes an implicit solution, and you can stop there if you want to. But let's do a little bit more because we can do better. So let's flip this x part to the other side, and then let's write like this. 1/2 x squared plus 1/2 y squared is equal to c. And then multiply by 2. X squared plus y squared is equal to 2c, and that's the equivalent form. Which do you like better? Well, to me it's push, but I like the following form better. This one looks very much like a known curve. What is it? X squared plus y squared equal to something. That's a circle. A circle centered at the origin with some radius, and radius should be r squared. So if I take this 2c as r squared, another constant, new constant, then you can rewrite it in the circle format. That looks better. Also, this c here, this constant here, that's an integral constant, yes, but it's not an arbitrary constant. It's not really arbitrary because you cannot have negative number here. You see? Flip this one over to the other side, then both positive and c cannot be negative. So just writing c will give you an illusion that it may be arbitrary. But here, if you rewrite it as r squared, then that illusion is gone. R can be truly arbitrary here because I'm taking square. Anyway, that's a solution. And that's a bit further manipulation. As far as the solution is concerned, this implicit solution up to here is concerned, that's straightforward. Separation of the variable and antiderivative computation. Now, the integral computation may become a little bit complicated depending upon how complicated your integral is. And you may have to use some different techniques like substitution by parts and so on and so forth. But the hard part is actually what comes afterwards. Analysis of solution. This one was just minimal, but there are some problems that you have to do a lot more than these. How about the next problem? Okay, let's do it. Oh, by the way, haven't we seen this problem before? I think we have. Let's go to previous lessons. Let's see. 01b and it's this one, isn't it? X squared y dy dx is equal to 1. Yes, that's it. And what is the solution? Well, this was the solution. And let's see if we can get that. In lesson 1b, we took a solution, we checked. Here, we are solving an equation to get the solution. Okay, let's see. Let's take separation of variable. All the y's on left hand side, all the x's to the right. Y dy is equal to 1 over x squared dx. Did I do this right? And then let's take the antiderivatives. So what do we have? What's the antiderivative of y? 1/2 y squared. What's the antiderivative of this reciprocal? And constant. Is everybody happy? Yes? No? Yes? Well, something's wrong. A very typical mistake I find often. This reciprocal function here is not really reciprocal. It's actually a power function. In fact, for this reason, I usually don't take 1 over something very much. I'd much prefer to do it this way. Take the negative power, and this is now x to the negative second power. Now it looks very much like power rule. So not the log function, I'm gonna get the power function here. Increase the power by 1 and divide by that power. And 1 over -1, that's just -1. So there goes the answer. And you can stop here if you want to. We want implicit solution only. Or you can flip this x to the other side. Let's go back here and just do it. 1 over x plus 1/2 y squared is equal to c. And there you go. There goes an implicit solution. So this kind of technique, separation and then taking the antiderivative, that's a key technique that you have to use for this course. Excuse me, did I say for this course? For this lesson, for separable equations. Of course, for this course, a heck of a lot more. Alright, those were 4 implicit solutions. Let's go to explicit solutions. We may have to do some more, and that more can get really messy in some cases. Okay, let's go to this problem. Let's see. Have you seen this equation too? I'm pretty sure you have. Let's see. It's this problem here. And one of the solutions should be this one. 1/16 t to the 4th power. And you could check that. But we're looking for general solutions here. So you're going to have to expect some integral constant here. Okay, let's go. Let's go ahead. And let's take the separation of variable. So flip this y to the other side and 1 over y to something. No, don't do it. This is better. If you use too many reciprocals, then it may confuse you. And then let's take the antiderivative of both. All right, this is very simple technique, separation of variable and taking the antiderivatives. And I intend to do this part very quickly because I'm assuming everybody is getting used to this very quickly, and they can just, all of you can just reproduce this part without any trouble. Okay, let's calculate the antiderivative. Raise the power by 1, and then we need reciprocal here because I have to divide. And then 1/2 t squared, and then I need integral constant. Division by 1, so let's remove that, and there goes an implicit solution. But that's not the end of the problem. We want explicit solution here, and after getting explicit solution or doing that process, we have to check the interval of definition. Okay, let's do it. Divide by 2, and then we have y to the 1/2 power equals 1/4 t squared plus c over 2. And then y is therefore, take the square of both sides. I'm forgetting something. Okay, there you go. And that's a solution, but what's the point of this c over 2? That's an arbitrary constant. Excuse me, I take it back. It's not really arbitrary. Generally, they may not be, but it's a constant it's an undetermined constant to be determined later. So it does not matter which character we use. So let's make it a little bit simpler. Different character, k is c over 2, and that way I don't have to deal with too many fractions. Let's say this is the end of the problem. Also, what's the interval of definition? Is that clear? Well, we have nothing more than polynomial functions, so it's got to be valid everywhere, and indeed it is. All right. Let's go to the next topic, and the next example here is Newton's law of cooling, but let me change my mind here. Let's do this one first. Radioactive decay model. This one first because this one's easier. Our textbook author does this one first and then this one later, but this was easier, so let's do easier one first. So, all right. The n dt is equal to negative lambda times n. And let's use the separation of variables. All the n's to the left-hand side, t's to the right-hand side. There's no t here, so you can consider this constant, negative lambda, or just 1, whatever you want to, is a t part. So we have 1 over n times the n is equal to negative lambda dt, and we can take the antiderivatives. Okay, what's the antiderivative of 1 over n? Log of n. And what's the antiderivative of the right-hand side? Negative lambda t, and then we need plus c, integral constant. By the way, do we have to worry about absolute value here or inside of the logarithm becoming negative? In this case, no. This one comes from radioactive decay model, and capital N is number of molecules, as a matter of fact. Number of molecules in terms of moles, and that's always positive. So I don't have to deal with negative numbers there. For part C, yes we do. Okay, all right. Let's solve for n. So n is therefore e to the negative lambda t plus c. And is that enough? Well, for this particular problem, yes it is, but we have to do better. We can do better, and we have to do better. Let me expand the font a little bit here. How do you manipulate it? This right-hand side can be rewritten like this. Like this. By exponent rule, if you have the same base, then multiplication is the same as adding up the power. And that's precisely what's happening here. And then e to the c power, we can rewrite it as another constant. Say k times e to the negative lambda t, like this. That looks better, but still we can do a little bit better. What is this k? Let's consider initial condition, even though this problem did not give you anything. When t equals to 0, which means the moment we began to measure the radioactive decay, plug in 0, what do you get? What is e to the 0 power? E to the 0 power is 1. So this whole thing is k, which means this number k is the initial value. So this can be rewritten as n0. So initial number of molecules times e to the negative lambda t is the number of molecules left in this exponential model of radioactive decay after t seconds or minutes or years later. I'll say this problem is done finally.